So when we get into 4.3, we're really going to investigate what we began in 4.1 a lot deeper. And I will just warn you guys, this is not a short section. It's not that there's so many ideas, it's just that the problems tend to be a little bit lengthy and need a lot of explanation. But when you get good at them, once you've had practice with several homework questions, then things get a lot faster. So hey, let's check it out. 4.3, it's called the shapes of graphs. And well, what we're asking is that question right there. What can derivatives tell us about the graphs of functions or about graphs? Okay, so we're going to start with this increasing, and we'll look at decreasing as well. So we're going to be able to tell based on a function's derivative where it is increasing and where it is decreasing. And so now this probably doesn't come as much of a surprise. We've talked about this a little bit here and there, especially when it came to graphing derivatives. If a function is increasing, that means its derivative, f prime of x, is positive or greater than 0. So as you look at my little sketch there, so this is the graph of f of x. So if it's increasing, right, and we always look from left to right. So if it's going up, then what's happening with the slopes of the tangent lines? Well, any tangent line we draw at any point is going to have a positive slope. So we know our first derivative would be positive if we're increasing. And likewise, if the function is decreasing, like in my drawing, then the first derivative is going to be negative or less than 0. So as this is decreasing, again, always looking left to right. If you were to draw any tangent line there, the slopes would all be negative slopes. So the first derivative is negative anytime you are decreasing. Okay, here's what we're going to do. We're going to develop a test to find, I'll just show you the whole thing, a test for when any given function is increasing or decreasing. So we'll call it the increasing/decreasing test. Okay. So number one, that looks familiar, right? We started that. We defined a critical number in 4.1. So step number one is to locate the critical numbers. If you remember, those are the x values where either the derivative equals 0 or where the derivative does not exist. Okay, so once you have the critical numbers, then we're going to mark those criticals on a domain line. So we're going to think, what's the domain of our function? And we're going to think of that like a number line. And we're going to mark off all the critical numbers on our number line or our domain line. And step 3 doesn't make a lot of sense until we get into the example. We're going to test a value from each interval in f prime of x. So when we mark off those critical numbers, that's going to create several intervals on that domain, and we're going to test each one. So what does that look like? Okay, we need an example for that. Let's try this right here. This will be a good one. Nice polynomial to get us started. We'll do more difficult things as this section progresses, but let's start off nice and easy. Okay, the example says find the intervals of increasing and decreasing. Where is that function increasing? Where is it decreasing? Okay, f of x equals 2x to the third plus 3x squared minus 12x. Okay, so if you remember, in the step number 1 was to find the criticals, and that actually has steps within itself, right? So to begin to find the critical numbers, we need to know the derivative. So there we go, f prime of x here equals 6x squared plus 6x minus 12. And to continue, we'll need to know these two things. When is the derivative equal to 0? What x values? And any x values where it does not exist. So I've just got these side by side. I'm just going to show you all my work here. So setting it equal to 0, Well, then we can factor out a 6. We can continue to factor, and without really talking through the details there, we've done this plenty of times up until now. X equals -2, x equals 1. And if you look at when does the function not exist, are there any times, any x values where the derivative does not exist? No. We've got a polynomial, so the answer is none. We're never dividing by 0, anything like that. Okay, so we've got our two critical numbers here, x equals -2 and x equals 1. So now we get to step 2, where we mark these on a domain line. Well, before we mark them, we need to ask ourselves, what is the domain of that function, f of x equals 2x to the third plus 3x squared minus 12x? Well, here, a polynomial, the domain is always all real numbers, and that's the case for us. Again, we'll look at other things. Typically, the vast majority of the functions we look at, the domain is -infinity to +infinity, all real numbers. And it's perfectly okay if you don't write this on your page while you're doing this work. If you can clearly see that's the domain, no need to write this. But it's not, once in a while you'll get a problem where, maybe there was division by 0 or something and something's not included in the domain. But again, the vast majority of things, that is going to be the case. Okay, so we know our domain is -infinity to infinity. We're going to mark those numbers on that domain line, and well, it's really just the number line in this case. So we're marking, got my number line, the whole thing. We're going to mark off -2 and 1. Now what's important is, you don't have to mark like 0 or anything else, just mark those numbers. But do put them in order, right? -2 comes first, then 1. That's important. Okay, so that's step 2. Mark these numbers on the domain lines. What was step 3? Test each interval in f prime of x, right? What is that? All right, so after we've marked our criticals, you notice, okay, these criticals divide this domain into 3 smaller intervals, right? There's -infinity to -2, -2 to 1, and 1 to infinity. So what we're going to do is pick a number from each interval, and we're going to plug it in to f prime of x. And that's going to tell us where our function is increasing and where our function is decreasing. Now, the way this works, you can take any number, any one number in each interval. So a good choice here might be -3, and that's what I'm going to pick, just to keep the values low. But you could pick -10, you could pick -100, you could pick, decimals or fractions if you wanted, so long as they fill in here. But I recommend whole numbers if you can. It's not always possible, but if you can, a whole number, and maybe -3 just to keep the values low. Okay, so just to kind of indicate what I'm doing for this interval, I'm going to pick -3. What would be a good choice here in the middle? A great choice is 0 for that middle interval. -1 would be fine, but let's go with 0. And then out here, again, keeping the values as small as possible, I'll go with 2. Now you could pick 10 or 100 or, you just need one representative from each. And then we're going to plug these 3, one at a time, of course, into f prime of x. And I've done that right here. So I'll let you guys take a look at that. So let's see. What was our derivative function again? Oh yeah, it's right back up here. There's f prime of x. And so I'm plugging these in. So I got f prime -3, 6 times -3 squared plus 6 times -3 minus 12. I encourage you guys double check my work. I got 24. Okay, so what is that? Like What's the big deal? 24. How, like, what do we do with that? So it's not so important what the number is. It's just, is it positive or negative? So this is positive. So we know the derivative here is positive. So I'm going to put a plus sign. Now, the way the logic works, any representative will tell you what happens on the entire interval. So if you were to pick negative 10, it would also come out positive, right? How do we know that? Because it doesn't become 0 until you hit negative 2. That's when the derivative is 0. So if it doesn't become 0, then any one representative represents everything. All right, I'm probably saying too much. Let's go on to f prime 0. That turned out to be negative. Not so important that it's negative 12, just that it's negative. So I'm going to put a big minus sign right there. And I like to circle it. And then we went back to positive for f prime 2. Came out to be positive 24, so I'm going to put a big positive there. Also, no coincidence that we got this symmetry that's fairly common, that sort of thing, that we got 24 again. But the point is positive answer, negative answer, positive answer, positive, negative, positive. Okay, perfect. This is where my derivative is positive, there and there. That's where my derivative is negative. I can answer this question. I squeezed it into the bottom of my page here, but there it is. We are increasing from negative infinity to negative 2, and then again from 1 to infinity. So I'll put that union in the middle, negative infinity to negative 2, union 1 to infinity. And we are, I should say, this function is decreasing just there in the middle between negative 2 and 1. So there is the interval of decreasing. We got our answer. Okay, I think I will stop this video right here. More to come.